Hello guys, today we're going to be doing electrochemistry. This is a lesson for grade 12 learners since they cover this chapter in term number 3. So it is an extension of redox reactions. I've attached the link on this video that takes you to that lesson because it forms the basis of what we learn here today. Now, in electrochemistry, we're simply trying to study the relationship between electricity and chemistry. Is there even a relationship? We are about to find out. So now, in this chapter, we simply learn that electricity can get some chemical reactions to occur, reactions that wouldn't happen otherwise. So we use an electrical current to force those reactions to happen. We also learn that we can use chemical reactions to produce electricity. So there is a vice versa relationship between electricity and chemistry. This can produce that can produce this. Now, in electrochemistry, we're simply studying the energy conversion of potential energy from electrical to chemical or from chemical to electrical. So to study this conversion of energy from electrical to chemical and chemical to electrical, we're going to look at two cells, namely we're going to look at the galvanic cell and also the electrolytic cell, using what we have learned on our previous lesson, redox reactions. So this is our prior knowledge. This is what we remember as we need to study the chapter. So these are batteries, the galvanic and the electrolytic cell. So we understand that a battery have an EMF. Even when you study the circuits, we always say that the battery have an EMF, the electromotive force. So to calculate the EMF in the battery, we say that the total standard potential will be equal to the standard potential of the cathode minus the standard potential of the anode. The E is the standard potential. So this is the voltage equation that calculates the EMF in these batteries, in these cells. Now, let us go over each of them. We're going to look at a galvanic cell, which is known as a voltaic cell. Now, let us look at some of its properties. Okay? So we have an energy conversion under a galvanic. Remember, we said we can move from electrical to chemical or from chemical to electrical. So what is happening under a galvanic cell? We are simply using chemistry to produce electricity. So under a galvanic cell, we have the energy conversion from chemical all the way to electrical. And then I also want to mention that since we are gaining or since we are producing electricity, our EMF under a galvanic cell will be positive. The E naught will be greater than 0. We understand that values which are greater than 0 are positive. So the E naught will be positive as such. Now, let us go back to that formula. For us to get a positive answer, this number should be bigger than that. So we need to conclude that under a galvanic, the E for cathode should be greater than the E for anode. The standard potential here should be greater than this one. So the inequality sign here has to be like this. The standard potential of the cathode should be greater than that one of an anode. If this is the case, when you substitute here, you will get a positive number as concluded above. So an anode is given a special name in this chapter. So the electrode that is called an anode is given a special name. So I've defined an anode on the previous chapter and the cathode. So the anode is given another special word here. So we call this one a reducing agent. A reducing agent. An agent is simply someone or something that facilitates a process or an event to ensure that it happens. So now the anode will ensure that reduction happens. Okay, and I need to mention that the anode will simply be the metal that is positive, that is negatively charged. So when we have negative ions, we call those N ions. So on the anode, there are N ions. The ions that are found on the anode are called N ions. And we know that these ones are negative. And then we call a cathode an oxidizing agent. We say this one is an oxidizing agent. An oxidizing agent. And an oxidizing agent will have the positive ions in this case under galvanic. So it will have the positive ions, which we call cations. The cations, and the cations are positive. I don't know if you see this, but under galvanic, you're gonna have a anode N ions, and you know that N ions are negative, C. So now cathode and cations, and you understand that cations are positive. So one of the major properties of a galvanic cell. So this will make us quickly identify a galvanic cell if it is present. A salt bridge. So what is a salt bridge and what does it do? So the main specific uses of the salt bridge under the galvanic is that it has to neutralize the excess ions. So it neutralizes excess ions in the electrolyte. It simply neutralizes the excess ions in the electrolyte. I will explain this once we see the picture of a galvanic cell. Now, another specific purpose of a salt bridge, it is simply to complete the circuit. So it completes the circuit. It completes the circuit. So this whole thing is happening inside a small battery, your normal battery that you know, like this. I think you've seen this battery. So you find that this side is positive and the other one is negative. So inside this battery, there'll be this setup. All of this is happening. So now, inside that battery, which we call a galvanic cell, we have two half cells. I hope you remember a half cell from the previous reaction. So now we have two half cells which are connected by that salt bridge, okay? And then as we continue, we have what we call a cell notation. So the cell notation under a galvanic will always be in this format. We have an anode, and then we bring the salt bridge. So this double stroke here represents a salt bridge, and then you put on your cathode here. And then I think this one will make sense because we've defined oxidation, we know anode. Remember that when you say an ox, you know that anode is happening under oxidation, and oxidation is the loss of electrons. So the electrons will always move from anode all the way to cathode. Now let us design a galvanic cell using silver and copper and try to interpret what happens in that galvanic cell. So this is a typical structure of a galvanic cell. Remember, we said it will have two half cells. It is a half cell when there is one electrode inside the solution. So we have two half cells and we have electrolytes in these solutions. Okay, this is what we call a salt bridge. This is the salt bridge. Okay, that neutralizes the excess ions in the solutions. And then this is simply a wire, a conductor, where the electrons will be moving from one atom to another. But we're gonna check the direction of the electrons here and just try to explain a lot of things about a galvanic cell. Now, when this happens, we should know where is oxidation taking place and where reduction is taking place. Now, we have silver. We have a silver electrode and we have a copper electrode. So we should know in which electrode is the oxidation taking place and which is the reduction taking place. We have what we call the standard potential table. It will be provided for you in an examination. So how does it look like? So the standard potential table looks like this. This is the structure of a standard potential table. There are a lot of things here. There are voltages of these elements and there are reactions. So the four reactions that you see here are all reduction half reactions. So when you write the reverse reaction here, you're actually writing the reaction that happens for oxidation. So why do I say these represent reduction? It's because we can see the electrons are on the left. If the electrons are on the left, then reduction is taking place. But if you write the reverse, the electrons will now be on the right hand side. Now, we're simply comparing here silver and copper. So on the standard potential table that I just showed you, you're going to find these values for silver and copper. So we said the bigger value will always be reduction. So we can see that silver has a bigger standard potential. So this is undergoing reduction. So let me just write red cat, and also write rig, because this define reduction and we know the electrode that is present here. So that means by default, the other one, which is smaller, will become oxidation. So that means I'm going to write an ox here, because the anode, the electrode that is under oxidation, is called an anode. And I'm going to define oxidation as oil. Okay, so now we said this is undergoing reduction because it has a bigger standard potential, and this is undergoing oxidation because it has a smaller standard potential. So let us write down our half reactions that are taking place here. So how do we write down the reactions? So let's look for copper and silver. We're going to write down the reduction first. The reduction is silver. Let us look for silver. There is silver. There is silver, and there is the standard potential, the 0.8. So let's write down the reaction for silver. We said it's undergoing reduction. Silver is undergoing reduction. For reduction, you always take the fourth reaction as it is. So this will be Ag plus an electron producing a silver metal. And then that means this one is undergoing oxidation. For oxidation, you always write down the reverse reaction. So now, because of this 2 here, that means this copper has a charge of 2+. So we're going to look for the copper with a 2+, because we have too many of them. So we have this copper, which is having a plus, and this one have a 2+. So we're going to take the one with the 2+, because we can see that 2 there. So now we're going to write down the reverse reaction. So the reverse reaction for copper is simply a copper producing Cu2+, as we said we're going to take, and then 2 electrons. Now this is our reduction half reaction and oxidation half reaction for whatever that is happening here. So let us come back here. We said this is the red cat. So this is the cathode. This is where reduction takes place. And this is the anode, and ox. Okay, the anode where oxidation is taking place. Do you remember we said Cc for cathode and cation ions? So this is our positive electrode and this is our negative electrode. So what is the direction of electrons? We said the electrons will always move from anode to cathode. That means the electrons will be transferred in this direction. So if this is losing electrons, this is what we're going to end up seeing, the gain in mass. I've covered this chapter that when you gain electrons, you're going to gain mass. And if this is losing electrons, it's simply going to decrease, maybe like this, to show that there is a corrosion that is taking place here. Now let us continue to answer more questions here. So we have written our reduction and oxidation half reactions. Let us write down the net. So what will be the net equal to here? So remember, we should ensure that our electrons are balanced. So to balance these electrons, I multiply this reaction by 2. So I now have 2, 2, 2. The electrons are now balanced. They are equal. 2 electrons, 2 electrons. And once this is the case, the electrons will always cancel out. Now, what do we do after cancelling the electrons? We write down whatever remains on the left-hand side on both reactions. So on this reaction on the left, we have 2 Ag plus, and then on this one we have a Cu, and then it produces what remains on the other side. We have a 2 Ag, and then also we have a Cu2 plus. Remember, the electrons are now cancelled. So this is what we call the net ionic equation. We might be required to calculate the standard the EMF of the cell. So remember to write this word in full: reduction minus oxidation, cathode minus anode. So these formulas are provided for you in the formula sheet. So please copy them as they are. Now, we did say that for reduction, we have 0.8. We're expecting a bigger answer, so the bigger number should be here. And then minus a 0.3. So this answer will be a 0.34 if I'm not mistaken. So let us punch this in the calculator. So we're getting an answer of 0.46 volt, and our answer is positive. That means our interpretation of whatever we were doing here is correct, because it leads to a positive EMF. If this EMF was to be negative, that means everything here is swapped around. Okay, go back and just swap around everything you've done. So that means your reduction is oxidation, your oxidation is reduction. And once you do that, you're going to find this answer positive. So when you get here, you can confirm a lot of things if your interpretation was correct. So the cell notation, how do you write down the cell notation? The cell notation is written in the following way. We said it's the anode and then the cathode. Now, which one is the anode? Oxidation. So we're moving from a copper, and this copper, we can see it's a solid, and then it changes the phase, it becomes a copper 2 plus. So the only thing we don't write here on the cell notation are the electrons. So you simply write down that you moved from a solid all the way to an ion of copper 2 plus, and then this we call the phase change. Okay, and then we bring back our salt bridge, and then we write down the cathode. So I simply wrote this in the order that I see: copper 2 plus. So I'm going to write this as Ag to Ag. Okay, Ag plus to Ag. But don't bring back the numbers that you used to balance. So this is Ag plus. I move from Ag plus all the way to Ag. So now this one is an aqueous solution. And my ions, they form part of the aqueous solution. This one is a solid. Apologies. And this is our aqueous solution. This is the end of this lesson.